Welcome to a quick lesson on using what we figured out about inclined planes and force formulas actually in a problem-solving context. So this is from the problem set that we have in the workbook. As always, solutions are available linked from the syllabus, but just seeing this done live might be helpful. So in pretty much all of these problems, we have a setup where an object is on a surface that has been tilted by some angle. In this case, they have told us that it's 27 degrees. And when it's tilted at this angle, the force normal, the force perpendicular to the surface, ends up getting tilted, and gravity ends up pulling straight down. Now, if we have no friction, these are all the forces. In this one, it says there's a frictional force. Well, friction is always parallel to the surface. And if the child would be sliding down, then friction will oppose that motion. Now, this looks like it could be a really nasty situation to deal with, but what we're going to do is change our perspective as if we are parallel to the surface ourselves. So looking at it, so out of the surface is straight up, down the ramp is left, up the ramp is right, and so on. And in that context, we can take gravity and split it into components. I'm keeping these two forces because those were, from this tilted perspective, normal force is up, friction is just sideways, but gravity can be replaced with components that are down the ramp, parallel to the ramp, FG parallel, and into the ramp, FG perpendicular. And we know, we are going to just tell you to use formulas, memorized formulas, that FG parallel is force of gravity, or mg, times the sine of theta, and that FG perpendicular is mg cosine theta. So it's easy to get mixed up on these, and it's why just doing a memorization is useful, and not getting stuck in something. This is, like I said, not many formulas that we like to encourage memorization on. These are pretty handy, because if we do that, we can notice what's going on here of, all right, force in one direction minus force in the other, force in one direction minus force in the other. It makes it easy to get usable net force equations. So parallel to the surface, I have the force down the ramp, FG parallel, minus force of friction equals MA. Perpendicular to the ramp, we have FG perpendicular minus normal force, or normal force minus FG perpendicular, either one, equals MAY. And this is the big thing here, because our object is not going into the ramp or out of the ramp. We get a setup where the y acceleration is 0, and we have one equation that is related to the only acceleration we're going to have. Acceleration in this context will either be down the ramp or up the ramp. And so we're getting it all into the x, and in the y, we get a pretty simple setup showing us that normal force is going to equal FG perpendicular, which we have already determined an equation for, a formula for, mg cosine theta. Okay, so I've given the quick rundown on what this looks like in a tilted setup. Let's look at the questions actually being asked. What is the weight of the child? Well, that is actually just asking what is the overall force of gravity, which is just mg, which is 150 newtons. These components that we're coming up with, these must be less than 150 newtons. What is the normal force on the child? Well, we have a formula for that, where normal force of the child is going to be our 15 times about 10, or 150, times cosine of 27 degrees. So normal force on this child is going to come out to be pretty much 134 newtons. 134 newtons out of the ramp. So, okay, we've answered that question. What about the net force on the child? Well, we have already established that the net force perpendicular had to be 0, but we did have force parallel. So our force parallel was FG parallel minus force of friction equals MAX. And let's look at the information that they gave us that could go in here. They have told us that the friction force is 56 newtons. And we can quickly do a calculation that FG parallel being mg times the sine of theta, when I do my plug and chug, that's going to come out to be about 68 newtons. So now, for our net force, we have these two. That's enough to get our net force. We get 68 newtons minus 56 newtons. So the net force ends up being 12 newtons down the ramp. Okay, next question. What will be the acceleration? And that should be the question that follows right after net force because, hey, the net force was equal to MA. So if 12 newtons equals MA, our acceleration then was going to be 12 newtons divided by the mass, 15 kilograms. And so that acceleration, 12 over 15, is going to get me about 0.8 meters per second squared. Last two questions. After 3 seconds on the slide, what will be the speed of the child down the slide? So I'm writing down here V final as an unknown. If the time is 3 seconds, the acceleration we know is 0.8 meters per second squared down the slide, and the V original was 0. And the whole reason we have this question in here is to just say that all our usual methods that we've done, once you get past those force of gravity components, then our usual methods of analysis will work just fine. So I could take my acceleration and my time, and so 0.8 meters per second squared times 3 seconds does get me 2.4 meters per second by the time the kid is getting to the bottom of the slide. Finally, the last question was, what is the coefficient of kinetic friction? So for mu k as the unknown, well, our equation was that kinetic friction equals our coefficient times normal force. So mu then will equal our friction divided by normal force. We have already been given that the friction is 56 newtons. The normal force we calculated not too long ago was 134 newtons. And so our coefficient ends up being about 0.42. So again, these last two parts going, hey, once we get past this thing, once we've used these, this is pretty much a force problem, just in line with what we have done in our force unit. All right, good luck. Please come in, check solutions, and ask questions, and we will look forward to seeing you. Happy physicsing.